Swayam Prabha. Digital India. Educated India.
So in the last lecture, we discussed about design of packed column for dilute mixtures. So the assumption of dilute mixture makes us to assume that the liquid and the gas flow rates are nearly constant across the column, and that we can use a linear equilibrium line, and that the F type and K type mass transfer coefficients can be used. Okay, so these are some of the approximations we can make when we deal with dilute mixtures or dilute solutions. Then we showed that the height of the column is written in terms of two components, one that involves the number of transfer units and the height of the transfer units. Okay, so this HTOG, or in short known as HTU, is the height of transfer unit, and this was defined as KY, G by KYA, where G is the molar flux of the gas. Okay, G should be in the units of moles of solute per unit area per unit time. This area is the cross sectional area of the column. KY is the overall gas phase mass transfer coefficient, and A is the interfacial area available for the mass transfer, which is a characteristic of the packing material. Total interfacial area per unit volume of packing. And this HTU, it comes with this OG here because it is based on the overall gas phase mass transfer coefficient. Okay, if you were to do the same calculation based on the liquid side mass transfer coefficient, you would have HTOL based on the liquid side mass transfer coefficient. But here in absorption, we assumed that the gas phase mass transfer coefficient is the important one. Okay, gas phase is limiting the transfer. Now the second component is NTOG. This is the number of transfer units with respect to, again, overall gas phase mass transfer, and this is defined as integral from y2 to y1 dy by y minus y star. So in the absorption column, y1 is the mole fraction of the gas, the mole fraction of the solute in the inlet gas, and y2 is the mole fraction in the exit conditions, and y star is the equilibrium composition. So y minus y star is the driving force available for gas phase mass transfer. Okay, now when we assume that the gas mixture and liquid mixtures are dilute, we can actually analytically calculate this integral, which is what we did in the last class. Okay, so if you do that, we showed this NTOG can be written as A by A minus 1 ln of y1 minus mx2 by y2 minus mx2 1 minus 1 by A plus 1 by A. Where this A is called the absorption factor. And this is defined as L by mg, where L is the molar flux of the liquid, G is the molar flux of the gas, and m is the slope of the equilibrium line. Okay, essentially this is absorption factor basically signifies the ratios of the operating line to the equilibrium line. Okay. So the way you would actually design this problem, you will do the calculation is that you are typically interested in calculating the height of the column. We already know how to do the diameter column calculation based on the pressure drop. Okay, so now we are coming to the calculation of the height of the column, in which case it involves two steps. First, involving the mass transfer rates and interfacial area via the height of the transfer unit, and next is the calculation of the number of transfer units, which kind of takes into account of the average driving force available, right? Any questions so far? Is it clear what we have done so far? This is the simplest thing you can do, right? From now on, things are going to get a little more complicated. Okay, especially when you go to concentrated mixtures, stripping, and so on. Okay, so we have to be absolutely sure that we understand this. Okay, any sort of confusion, misunderstanding here in this particular treatment? So one way to check if you understand this correctly or not is to do a problem. Okay, this will actually become the part of the tutorial sheet. Okay, so tutorial problem will be uploaded, in which this problem will feature in. Also we'll have additional problems. Okay. Okay, so the question goes on something like this, that in a bioprocess, a molasses is fermented to produce a liquor containing ethanol, okay, or ethyl alcohol. A CO2 rich vapor with a small amount of ethanol is evolved. Okay, so basically you have a gas which is mostly CO2 but also contains some amount of ethyl alcohol. The ethanol is recovered by absorption with water in a packed column. Okay, so that's the overall problem. Now they have given some information. Entering gas 180 kilomole per hour, which contains 98% CO2 and 2% ethanol, and its temperature, pressure are given. The entering liquid is 100% pure water. Okay, no CO2 no ethanol in the inlet stream, also happening to be at the same temperature and pressure. The required recovery of ethanol is 97%. Okay, the inlet stream contains 2% of ethanol. In that 2%, you have to remove 97%. You have to remove. Okay, so that's a design specification. And the packing involves 1.5 inch metal pal rings. Okay, which means you will know how to calculate the pressure drop, you know how to calculate the interfacial area once you know the information about the packing material. The K value of the ethanol based on Raoult's law at 30 degrees Celsius and 110 kPa is found to be 0.57. That means we know about the equilibrium line, okay, which is a straight line. Compute the required packing height if HTOG is 2 feet. I already said if you want to calculate the height of the packing, you need to calculate the height transfer unit and number NTU and HTU. HTU in this problem is already given, which means mass transfer coefficient, interfacial area, all that is actually kind of already calculated for you. Okay, so all you need to calculate is the height of the column. So the height of the column Z is given by HTOG times NTOG. So this is given 2 feet. And if you can calculate the number of transfer unit NTOG, then we know what is the height of the column or height of the packing. So let's also mark the information that we know from this problem in a diagram. So here solute is ethanol, and whenever it's given in terms of percentage, it's mole percent. Okay, so this is going to be 0.02, and Y2 is 3% of 0.02, because 97% has to be removed, then the remaining concentration will be 3% of the inlet concentration, which is 0.02. So essentially Y2 is 0.006. For the liquid, inlet liquid, it's pure water. X2 is 0, X1 is here, and G is given as 180 kilomole per hour. So we are going to make an assumption that this is a dilute mixture, for which I know the formula for NTOG. Okay, NTOG is A by A minus 1 ln of Y1 minus mx2 by Y2 minus mx2, 1 minus 1 by A plus 1 by A. So what are the things I know here? Do I know A? What is A? A is L by mg. M I know, G I know, but I do not know L. Okay, so L is unknown. What about the terms inside this logarithmic term? Y1 we know, Y2 we know, M we know, X2 also we know. So that means only thing that we don't know is A, because we don't know the liquid flow rate. Okay, and this is one of the ill-posed problems, right? L is not known. So the height of the column that you will calculate will actually depend on what the L you are going to choose. So how do we go about from here? I didn't set this problem, okay? So in case if you are thinking that I am the reason for the ill posing the problems. See, if you think about it, you could say, well, I don't care, I can just choose whatever L I want. Maybe make it L equal to G, right? I know G, it's about 180 kilomole per hour, I make L also the same, right? That's one choice. Or can you also make a little bit more smart way of choosing this? I mean, there is no right, wrong. I mean, like I said, it's an ill-posed problem. There is no right answer here. Okay, all answers are going to be right here. But what is that we can do? You have to think a little bit carefully how we can make this choice of L. Do we have any guiding principle here? Do we have equilibrium line? Yes. You are saying that we can calculate the minimum. Okay. Okay. So let's say you do at minimum. Okay. So what that means? So graphically, what this means is that you have X here, you have Y here. So this is our equilibrium line. Y is equal to 0.57x. So where do I mark my operating line? Y2 is somewhere here, which is 0.02. X2 is 0. So my point is somewhere here. Where is my Y1? Y1 is somewhere here. Sorry, actually it's the other way around. So Y2 will be 0.0006 I mentioned. Y1 will be equal to 0.02. So the operating line should lie somewhere on this line, right? The operating line will lie somewhere on the dotted line depending upon the liquid flow rate that you choose. If you choose the liquid flow rate, then you are actually fixing the slope of the operating line, right? So you could say, well, I have a line something like this. I can have a line, or I can have another line here, or I can have another line. There are multiple choices. So depending upon the liquid flow rate, the corresponding composition of the outgoing liquid will be determined. Okay. Secondly, the average driving force available also will be different based on different slopes. Okay. For example, if I take this one, the driving force is actually these ones. These lines are the driving force. If I chose this particular line, then the average driving forces are these. So by choosing L, there are so many things we can do. I can change the slope of the operating line, I can change the average or the driving force available for the mass transfer. I can also control the exit liquid composition. Okay. So now which way to go? Okay. He was saying, well, we will do this for minimum liquid flow rate. We know how to calculate minimum flow rate. So I'll just delete all this. So minimum would be something like, so the minimum is one where the outgoing liquid is in equilibrium with the incoming gas. Okay, and we can calculate this. I know all the information. So this would be the slope corresponding to LS minimum. Okay. Now you can do this, but little bit be careful about this. Let's say you find this LS minimum and then you go to calculate A, I call it A minimum, right? And then if you go to this logarithmic term, you will see this term will blow up, because when you go close to this point, the average driving force vanishes. Very close to the equilibrium line, the average driving force y minus y star will vanish, and because we integrated the inverse of y minus y star, so this term will actually diverge. You will get something like ln of close to 0, something like that, okay, which is not very physical. So we should not choose the minimum liquid flow rate, but it gives us an idea what should be the minimum that we can use. Then we can say, well, I'll take 50% more, 100% more, 200% more. Okay, that's our choice. But at least instead of choosing randomly, you could choose based on the some factors of the minimum liquid flow rate, because we know how to calculate minimum flow rate. Okay, so that's what we're going to do. We'll first calculate the minimum liquid flow rate, and then we'll say 50% of that. Corresponding to that, I will calculate the exit composition, and I also say the height of the column is this if you choose 50% more than the LS minimum, right? Fair enough? Okay, good. That's all we're going to do. And I also wanted to highlight that the same thing we did for pressure drop calculations. We would say the maximum flow rate is determined by the flooding conditions. Okay, we would say what is the pressure drop corresponding to flooding, but we don't want to do it a flooding condition. We will say 50% less than the pressure or 20% less than the pressure. Like same way here also we are saying we are going to find the minimum flow rate and then scale it up by a factor. Okay, so you can see the analogy between why we need to think about this upper limit and lower limit. It basically gives you a kind of a range of operations. Okay, you can choose, okay, this is my minimum, I will choose some factor of that. And LS minimum is actually straightforward for you, right? I mean, you have already done this, how to calculate LS minimum. So I will directly give the results, but you can do a mass balance and you can find this out. So you will see the LS minimum comes out to be something like 99.5 kilomole per hour. Okay, and then I'll say my L is 50% more than L minimum, which is basically 149.2 kilomole per hour. Well, if you didn't care and you just said L is equal to G, you are still not too far off. Okay, G is 180 moles per hour and L is something like 150 mole per hour. Even if you say 180, it doesn't matter. It's a fair choice. Okay, if you don't care to do LS minimum calculation. So now that I know L, now I can calculate A. So A is 149 by 2 by 0.57 into 180. So this comes out to be something like 1.45. Then it's straight for substitution. Okay, so you're going to go back to this equation, substitute for A, y1, y2 we know. Anyway, this mx2 term is 0, and the remaining thing is a mere substitution, and then you will see this NTOG that you get is 7.73. Now our Z is equal to 7.73 times HTOG, which is 2. So you'll get something like 15.5 feet. So this is the height of the column. An actual problem would be given that the mass transfer coefficient and the interfacial area you can calculate from the tables, and you should be able to calculate the HTOG also separately, but here it's given. Okay, but that's a straightforward thing to do. NTOG calculation requires a little bit of a thinking. Okay, that's all. Okay, so now what we are going to do, we will just do the design of stripping column. Same equipment, now the operation is switched. Instead of removing the solute from the gas to a liquid, we will do the reverse. Okay, we want to remove a solute from a liquid to a gas. Okay, so that is called the stripping operation. So design of stripping column. Again, we are going to use this dilute mixture concept. So note that we are still doing this counter current operation. Counter current, solute is recovered from liquid to gas. Okay, this is what we call as a stripping. So Z here refers to the column height. It is measured from bottom of the column. Okay, exactly same as the absorption column design. Okay, only the transfer of the solute is different now. We are going to make an assumption that the in the case of stripping, we will use the liquid phase mass transfer coefficients. Okay. When we did absorption, I said gas phase is limiting the mass transfer. In stripping, I am assuming liquid phase mass transfer is limiting. Okay. However, you can do a absorption column design with the liquid phase mass transfer controlled. Similarly, you can do a stripping column with the gas phase mass transfer control. Okay, these are 4 combinations, right? But here, for example, I am going to take liquid phase mass transfer coefficient controlling the mass transfer. So our approach is that we will take a very thin section here. So this point is at Z and this point is at Z plus dz. We are going to do a mass balance there. With respect to the solute, A mass balance or mole balance on a thin section dz, we are going to do it. So in this section you can see that this is a liquid entering here and this is a liquid leaving and this is the gas leaving and gas is entering here. So we will write something like in minus out plus generation is equal to 0 because we are talking about steady state operation. Okay, no accumulation terms. In this particular section, how many moles of A coming in, how many moles of A going out, how many moles are generated, and that must be equal to 0. Okay. So now we are doing this with respect to, let us say, the liquid phase. okay, because I said liquid phase is mass transfer controlling. So, I am going to deal with everything with respect to the liquid phase flow rates, liquid phase mass transfer rate and so on. So, what is coming in here? The coming in is L times X A at Z plus dz. This is the moles of A entering at location Z plus dz, okay, and this A here is the cross sectional area, not the absorption factor. X is the composition at this point, L is the flow rate of the liquid, and what is going out is here, that is L X A at Z, okay. This is the moles that is leaving that section. Now, this generation or loss is because of mass transfer. The liquid is actually losing its solute to the gas. So, instead of getting generated, it is actually losing it. It's a loss term, okay, and we can model that as minus Na times A dA, sorry, N A dz, and that must be equal to 0. Please note, Na is the mass transfer rate, which is always written in as a positive term. Some mass transfer coefficient times the driving force is always positive, okay. But here the liquid is losing because it's stripping operation. So, I have put a minus sign here because it is not generated, but actually it is lost, okay. And you can note this particular term where we have invoked the available interfacial area because of the packing, okay, which is given by this small a, which is the interfacial area per unit volume of the packing. What is the volume of the packing in this thin shell? That is nothing but A times dz. Capital A times dz is the volume of the packing I have highlighted here, okay. So, the total interfacial area available for mass transfer in that thin shell is small a times capital A times dz, and that is multiplied by the mass transfer flux Na. So, now what we can do, we can cancel the cross sectional area from this equation because that is a common term. This A goes, then we are left with Lx at Z plus dz minus Lx at Z, that must be equal to Na A dz. So, I am going to bring this dz on the left, and then I say in the limit of delta dz tending to 0, Lx at Z plus dz minus Lx at Z divided by dz can be approximated to be d of Lx by dz, okay. And then on the right hand side I have NaA dz, sorry, NaA, that is it. So, now we have to write explicitly what is the flux. So, flux Na is written as Kx into x minus x star. So, why I write this way? Because again graphically this is y, this is x. So, this is my equilibrium line, and the operating line for the stripping is like this, okay. So, this is my this is my x2, this is my y2, and this is x1 and this is y1, okay. This is the operating line. Now, here we are saying the mass transfer rate is given by if I take any point here on this line, the mass transfer rate there is given by x times xi, right. Xi is the interfacial concentration corresponding to equilibrium line, and this slope is this line is called the driving force line, whose slope depends on minus kx by ky, if you remember, and this is the local mass transfer coefficient based on the liquid phase. That is why this x means is a liquid phase. Or equivalently, we can use the overall mass transfer coefficient. Sorry, actually this is not x star, this should be xi. So here when I change the equations in terms of the overall mass transfer coefficient, then my driving force line is actually this. So this is the driving force for the liquid phase mass transfer, which is x minus x star. Okay, the difference is the following: if you use this xi, you are using the local mass transfer coefficient, small kx. If you are going to use the equilibrium composition x star as the overall driving force, you are going to use the overall mass transfer coefficient accordingly. Okay, is it clear? We have done this before, switching between the local mass transfer and overall mass transfer coefficient. Okay, so now we will go with this particular overall mass transfer coefficient approach and then substitute here. So we have d of Lx by dz is equal to kx a x minus x star. Because x minus x star is this term offering the driving force for the mass transfer here. So now we can separate these terms here and also make use of the fact that L is constant. So L comes out so you can see that we are still having a similar kind of formula that can be split into two parts. We will call this L by kx a as HTOL, that is the height transfer unit with respect to overall liquid phase. And this term dx by x minus x star from x1 to x2, we will call this as NTOL, which is the number of transfer units with respect to overall liquid phase mass transfer. So essentially this is our design equation. This is our design equation to calculate the height of the packing for stripping operation, which involves the calculation of HTOL and then NTOL. So if I know the liquid flow rate, mass transfer coefficient and interfacial area through the packing material, I can calculate the height transfer unit. And if I know about this average driving force x minus x star, I can integrate this out, I can calculate the NTOG also. Right. Now since we are talking about dilute mixture, this integral can be analytically done, which is what we are going to do now. So our calculation of NTOG okay. NTOL, yes, you are right. This is NTOL, yes. So again recall that if I have an x value here somewhere, the corresponding x star is somewhere here, right? This is the driving force, and this driving force I have to integrate from the bottom to the top of the column. Okay. So now I need to deal with this. This x here comes from my operating line. This x star is coming from my equilibrium line, right? Okay, so now we have to deal with this. So this point here is x comma y coming from the operating line. This point here having x star comma y. Note that these 2 points have the same y value, only x is changing, right? So that means if I have to know what is x star, I can actually calculate the x star from the y itself. Okay, so if I use y along this equilibrium line, the corresponding one is the x star. What I mean by that is x star can be now written in terms of the equilibrium line, which is y by m. Why this is important? Because this y is coming from again the operating line. So this can be written as x1 by x2 dx by x minus y by m, in which case both x and y have to be chosen from the operating line. Now we already know how to relate x and y from the operating line, because we can write a mass balance. I can get an expression relating x and y in the operating line. Okay, so what we have done is the equilibrium liquid phase composition is obtained through the equilibrium line using the gas phase composition, but here the gas phase composition is also from the operating line, because I said the y value here and here are the same. Whether I take the y value from the equilibrium line or from the operating line, it does not matter, because that remains the same, right? So to calculate x star, I am getting that from the equilibrium line, which involves the operating, which involves the composition of the gas phase in the operating line itself. So all I have to do now is write a mass balance equation for the operating line and then get this estimate. So going back to this kind of a stripping column here, and then we can write a mass balance. So we will do a mass balance to obtain the line for operating line in this particular envelope shown by a green line. So if you see what is coming in, L times x moles are coming in from the liquid side, from the gas side G times Y1 is coming in, and what is leaving is L times x1 and then G times Y, where x and y are the composition at this particular point, whereas x and y1 are the composition at the inlet conditions. In the case of absorption, I did a mass balance for the top of the column, but here I am doing for the bottom of the column. It does not matter. There you can do a mass balance for the lower part of the column. Here you can do the mass balance for the upper part of the column. It does not matter. Okay, just a choice that we are making here. So from here, what we want is we want the relationship between x and y, so that I can substitute for y in terms of x. Okay, so let's find out what is y by m from this equation. So y is equal to L by G x plus y1 minus L by G x1. Okay, what we want is y by m. So y by m is L by mg x minus L by mg x1 plus y1 by m. So what do we call this term L by mg? This is the absorption factor, A, not the cross sectional area. Okay, this is the absorption factor. You will be fair if you ask why should I define an absorption factor, why can't I define a stripping factor? Okay, you can put a symbol S and then define a stripping factor if you want, but then since the terms are the same, so why bother? Okay, so you write same, you call it as absorption factor even though the operation is stripping. Okay, so it just to kind of minimize the use of symbols, that's all. So I get Ax minus Ax1 plus y1 by m. Okay, so that is y by m. So now I am going to use this y by m term to calculate this driving force x minus y by m. So the driving force is x minus y by m, which is nothing but x minus Ax minus Ax1 plus y1 by m. So you have to see that this is actually a constant and this is only a function of x. Okay, so in my expression for the NTOG, or NTOL actually, so this is basically in the form that dx by some ax plus b kind of formula, right? Because this small a here is nothing but 1 minus a, this b constant is all these terms. So, and you know that this integral is actually 1 by a ln of ax plus b. You can use this formula to integrate this. So you will get 1 by 1 minus a ln of x times 1 minus a plus ax1 minus y1 by m, and this is estimated at the calculated at the limits x2 and x1. So this is the final expression, and so a little bit of simplification is further possible here. So I'll give the final equation, but this is something you can see it for yourself. So you have to be careful not to use this when a is equal to 1. Okay, this is valid only when a is not equal to 1. So like I said before, suppose if you have a is equal to 1, all you need to do is you have to go back here before you do the integral. Okay, if you substitute a equal to 1, you see this term will drop out, you are left with only this constant term. So if you integrate, you will get x1 minus x2 divided by this, just this. Okay, so that is for a equal to 1, NTOL will be simply x1 minus x2 divided by whatever the term x x1 minus y1 by m. Okay, so this is the case to be used for a equal to 1. Yeah, I mean I have a problem for this case also, but I think we don't have time to run through that, but we'll stop here. And just to give an update, what we have done is we have calculated the height of the column for a dilute mixture for both absorption and stripping. Okay, so in the next lecture I will talk about how to do this for concentrated mixtures, in which case you won't get this nice analytical result. It has to be done numerically or graphically. Okay, I will discuss one such example also. Yeah, okay, class is over here.